So what we're trying to do is go from having a consistent collection of sentences, right, to actually constructing a mathematical structure for those sentences in which they're true. So the main theme of today is, where do we get this structure from? We need something concrete. We've just got these symbol strings in these formulae or sentences, and I just know that this is a consistent set of sentences. But somebody is asking me to actually produce a model or structure or interpretation, these all mean the same thing, in which these sentences are true. So the neat trick is that we actually, we're mathematicians, we actually use the sentences themselves to build a structure. Okay? So that's what will come out today and how we're going to do it, right? It's a question in the definition of the completeness. Is the or inclusive or exclusive? When I say, I think inclusive or, I can never remember which way around that is. This will be, let me go through it. Theory is complete if for any sentence phi, well, for any formula phi, so I forget exactly what it says, sentence, either T proves phi or T proves not phi. Sorry, I haven't turned the camera on. Okay, so here is the question we're being asked. So the definition of complete says for any sentence phi, either T proves it or it proves its negation. Now it's possible that it could prove both, in which case T is consistent. Inconsistent. T is inconsistent. Right? But we allow this possibility. Right? If you've got an inconsistent theory, you can prove everything. So certainly you're going to be able to prove phi and not phi. You're going to prove psi and not psi for any other psi and not psi. So here we can say theory is complete. Well, it's tricky. It either proves this, or we could prove both. Right? In which case it would be an inconsistent theory and perhaps not so interesting. Right? It's a question about, will I release solutions to the exercises? Yes. And then the question that I can't quite understand, perhaps this is this question. Is not this the same as proves not, right? The answer is no, not at all, if that's the question, right? This is saying that the system is incapable of proving sigma. So we often write this with a line through it. It can't prove sigma. This is a positive assertion. It is saying that it can prove not sigma. So our rules from our axioms allow us to deduce not sigma. This is saying something that the system can't do. So these are very different here, if that's the question. Okay, if there was a question about releasing solutions to the exercises, so that's a yes. I'm still waiting for permission to give out the solutions to the assessed homework, if that was a question, was about that. And the solutions to the next set of homework will be released at the same time as the deadline for the ones to be handed in. So that'll be Thursday at noon. Okay. So we're in the middle of proving a major theorem, and this is theorem 417. This is what I alluded to when I was talking to you. Any consistent set of sentences has a model. Right? So a model is a structure in which the sentences come out true. Right? So here's a remark apropos what we've just been discussing. Well, I can't say if and only if. Delta does not prove a contradiction. So let's say some sigma and not sigma. If you're a consistent set of sentences, right, you're not going to be able to prove its contradiction. On the other hand, if you're an inconsistent set of sentences, you can prove everything, in which case this would fail. I could prove sigma and not sigma from delta. So another way of saying that I've got a consistent set of sentences is to say something like this. Right? Okay, that's an aside, right, from so let's continue here with the theorem. We did one stage yesterday, which was taking a consistent set of sentences and expanding it to a complete consistent set. So the Lindenbaum lemma which has a number 415. So that said, if gamma contained in a language is consistent, we can find the gamma prime extending gamma in the same language, which is consistent and complete. We had a fullness lemma. I didn't call it that. It's not called that in the notes. 423. And that said, if I had a consistent set of sentences, then we can expand the language by adding constants. writing infinitely many constant symbols. And so that we could then find, so there was some delta prime extending delta, where delta prime was in this slightly larger language. Here. And delta prime would be full. And what did that mean? That meant if I've got any formula like this for Vk psi, and if delta prime proved this string here, then there's a constant C. So that delta prime proves psi when I put in the constant for Vk. So it kind of gives a concrete witness to this existential statement. So, I mean, you know, number theorists, they might prove, you know, oh, there is a natural number such that blah, right? Well, if number theory was full, it would actually produce that number, or an example of that number, right? It wouldn't just say there is a number, it might say 23 as this property psi, right? So what we're going to do is use these alternately, infinitely often. We're going to start off with some consistent set of sentences that we're interested in, right? Some gamma, we will call that gamma 1. And we're going to alternately expand gamma 1 so that it satisfies the Lindenbaum lemma. We then make it consistent and complete. We then expand the language and make sure that it's full, right? But now we may have lost completeness. So we do the Lindenbaum lemma again. But then we'll have to, okay, find a full extension of that. So we go backwards and forwards between these two processes. I mean, set theorists would say omega many times, infinitely often. So then at the end, actually, when we take the union of all of these gammas that appear in this way, we'll have something that's both consistent, complete, and full. And from there, we can build our model. So that's the plan that's outlined on 76. Right? So what I just quickly sketched in words is done in lemma 424. So let gamma contained in L be a consistent set of sentences. Then there is some L prime containing L. And it's just an extension by constants. And there is some gamma prime containing gamma. Gamma prime in this larger language. So that, oh, well, I'll stick with the notation in the notes. It's called gamma star. So gamma star is consistent, full, and complete set of sentences in this larger language. In this L, again, this is called L star. Okay, the notes. Okay, so as I've said, let's call this gamma 1 here. Let's call this language L1. So we're going to start out here with gamma 1. It's in this language L1. So this is gamma, this is L over here. So we first extend it to be consistent and full. Okay, and then this will be in this language extension by constants L2. Okay, now I extend it this using the Lindenbaum lemma. Language here will stay the same. And I'll call this one here gamma 2. So now this is a complete extension of delta 2. So this here ends up being consistent and complete. But we don't guarantee that fullness is still holds. So we do this one again. We expand the language by constants here. And we apply that lemma. So now we have consistent and full here. So we just keep doing this. So in the end, we're going to have, something at the nth stage, we're going to have gamma n, delta n plus 1 contained in gamma n plus 1. This will be in language Ln. This will be an extension by constants in the next language, Ln plus 1. And this will be the same here. And from here to here, we apply Lindenbaum. And from here to here, we apply the fullness lemma. And gamma star will be the union of the gamma n's, which is the same as the union of the delta n's. Doesn't matter. And L star is the union of the languages. So actually, each time we only extended the language by countably many constants, and we only did it countably many times. So actually, L star is just the same as our original L, but it's just got a whole lot more constants in it. So it's still a countable language if L is. Right? Yeah. Now the point is that this guy is complete and full. So if sigma is a sentence now of L star, right, then well, it's a sentence in one of the languages. L star is the union of these languages. So if it's a sentence in this language, it's a sentence in some Ln, right here. But gamma n is complete, right? In the language, we want to be pedantic. So either gamma n proves sigma or gamma n proves not sigma. But then so does any larger set of hypotheses. So gamma star proves sigma or gamma star proves not sigma. So completeness is okay. Gamma star is full. So suppose gamma star proves there is some, I don't know, vk psi. Right? Holds. With now, psi is now in L star. And that's its only free variable. Here. Okay, a proof is a finite sequence of lines, right? So actually, only finitely many hypotheses are needed from gamma star to prove this. Gamma star is the union of the gamma n's. So actually, that finitely many hypotheses from gamma star, they're all in some gamma n for a large enough little n. Right here. So for some large enough n in the natural numbers, gamma n proves this. But then we dealt with this. When we went to delta n plus 1, we were then in a larger language where there was a constant to make sure that this substituting this constant in would make psi come out true. So for them, for some constant, d in the next language, we had delta n plus 1 proves psi with this constant in place of vk. Right? Because this was a full set of sentences here. Okay, delta n plus 1 is contained in gamma n plus 1. So gamma star will prove this. So gamma star is full as well. So those devices then allow us to go from a consistent set to a set that's consistent, complete, and full. So now we need to use this to construct ourselves a model. We do this by using the so-called canonical model, canonical interpretation. So we start out with a consistent set of sentences.
Sorry, Philip, there's a message in the chat.
Oh, yes. Can you please share the end of that last one again, everybody? Thanks. Thanks for pointing it out. I don't always have my eye on the chat box. I'm looking in several places at once all the time. Paper notes.
Do we need not to show
Yes.
that the gamma star is consistent?
Sorry, that wasn't quite loud enough. Could you repeat?
Do we have to show that gamma star is consistent, or is completeness and fullness enough?
I suppose it's true. I could have said a word about consistency. I mean, gamma star is a union of complete sets of sentences. So it will itself be a complete set of sentences. If from gamma star I could prove a contradiction, you would only need finitely many statements from gamma star to do it. So just like fullness, or completeness rather, I would be able to find some gamma n in which those hypotheses from which I could derive a contradiction would lie, right? But we know that doesn't happen because these are all consistent. Yeah, so I suppose, yes, that's true. It would be worth saying, thank you for asking that question. It's worth saying that gamma star is also consistent. So gamma star is consistent. So that's like complete. Yeah. Assume that the language has at least one constant symbol. That's just to kind of get things going. So the canonical interpretation determined by gamma is the following structure or model. I, maybe a subscript gamma, but this will stay fixed, so I'll just write this as I here. Structure I is going to have a domain, and we're now going to have interpretations for the predicate symbols that are there in this, and likewise interpretations for the functions that are there in the language, and constants, interpretations for the constants that are there in the set of constant symbols for the language. So here the language consists of the relation symbols, the function symbols. It's built on these three collections. So, as I said, the beauty of it is that we build this out of thin air. All we've got is this consistent set of sentences, right? So I is the set of equivalence classes of closed terms here. We have to say what this is. For a term t in the language, which has no free variables, we know there are such because we specified there was at least one constant. So I know there's something here. We didn't make any requirements on the functions and relations, but we did say there's at least one constant, so there's at least one closed term. And this will ensure that I is non-empty. And the equivalence relation is what we can prove to be equality. Equivalence relation, again, sub I. We're going to say that two terms are equivalent if and only if, from my consistent set, I can prove this equation. Our constants then, this will be, right, the equivalence classes of the constants that are like this. if I want to interpret my relation, maybe I've got here a n-place relation. So I'm going to relate the objects in I. I is going to be the set of these guys here. I'm going to interpret P amongst the objects of I here, if and only if gamma can prove P holds of T1 up to Tn.
Sorry, Philip, what's the difference between the I's that are underlined and the I's that aren't?
It's partly my laziness. I think of the thing underlined. I can't write boldface. So the thing underlined is the kind of like the algebraic structure, if you like. The thing without the underlines is just the domain of elements. It's just the set of elements of the
Brilliant,
structure.
thank you.
So it's kind of one of the components of the structure. So here are all the components of the structure. This is the name of the structure, and this is the name of the set of elements. That's all.
Oh,
So it's
thank
kind
you.
of, no, I mean, it makes sense to differentiate between these. I mean, I should be interpreting these things in the structure. So officially, I should put underlines underneath all of these things. But as you can see, I frequently forget. And it just becomes a bit tedious doing it all the time. And the interpretation of the function, again, if it's an n-ary function, maybe this equals something else. I call it t. If and only if gamma can prove f of t1 up to tn is t. So this way we can kind of populate the structure. The elements of the structure will be literally the equivalence classes here. And the relations are given here. So this relation holds amongst these equivalence classes if gamma can syntactically prove this. So NB, the domain here is not the empty set. Since we specified at least one closed term. Namely a constant was in the language.
So is there only one constant in every single equivalence class of constants?
No, it might, well, one might think, it might be that, no, it could be that gamma could prove that if there were two constants in the language, gamma might prove that C equaled D. In which case, we would say that the equivalence class of C is the same as the equivalence class of D. So we'd be saying this here. So it all depends what gamma can prove. Okay.
Is gamma consistent in this? Oh yeah, gamma is consistent.
Yes, gamma was consistent in the beginning. So we didn't need completeness and fullness of gamma to make this definition, but we do need completeness and fullness to get what we want, which is lemma 426. Let gamma now be complete, full, and consistent set of sentences. then for each sentence, sigma of the language, we have, when we look at this canonical interpretation, the sentence is true if and only if gamma could prove it. Here. So this is useful. Right? We've got a concrete structure in which the provable things come out true, and conversely.
Sorry, Philip, please can you show that last sheet again?
Sure. I'm only writing out what's in the printed notes.
Thank you.
Okay. This is something we can prove in predicate calculus without any hypotheses. So we have by fullness some C equals C. So the fullness really, I mean, it's slightly odd, implies there is a constant in the language. I mean, I only make that remark because the hypotheses of the lemma don't actually specify that there's a constant in the language, but actually the fullness implies that. So we prove the theorem by induction on the complexity of the sentence, sigma here. We need this to be proved, this thing here to be true for all sentences.
Sorry, Philip, do you mind moving your page to the left slightly?
Sure. Thanks. So this is proven by induction on the complexity of the sentence, sigma. I emphasize that it's a sentence, not a formula here. Okay, so what could it be? I've called it a phi in the notes, so let me stick with phi here. So perhaps phi is atomic. Then actually this is just part of the canonical interpretation. This is just in the definition of the canonical interpretation, I sub gamma. Because what do I mean by that? After all, right, this equation is an atomic formula. Right? So I have that in the interpretation, right, this is one object, right? This is one equivalence class. Right? Likewise, I've gotten this atomic formula here. Right? This holds in I if and only if gamma can prove it. If and only. Likewise, the value of the function. So for these atomics, it's just the definition of I. So this is then just the definition of the canonical interpretation I gamma. Since the denotation of T in the structure is just this equivalence class. So, for example, gamma proves T1 equals T2 if and only if, right? They're equivalent in that sense, which we gave. But that just means that in the structure I, now think that, right, T1 equals T2. Should put here I's, right? These equivalence classes. So that isn't an issue. Maybe phi is not psi. Okay, so
Sorry,
phi
could
is
you move
sorry.
the page down slightly, please?
Yeah.
Thank you.
Yeah, I do tend to go off piece. So phi is a sentence, psi is a sentence. So the structure is a model of, not psi. If it's not the case, the structure is a model of psi. Now we use the induction hypothesis. So it's not the case that gamma proves psi, because now psi is less complex than phi. So I can use the induction hypothesis here. But gamma's complete. So if gamma doesn't prove psi, it proves not psi. So that's the equivalence we wanted between this and this. And for implication, it's similar. So I'll just leave that exercise, if you like. Psi. Let me just do the more difficult case first. Case 2 is when this is a sentence, but psi may have free variable VM. So psi may not be a sentence. This is a sentence because the free variable gets bound by the quantifier. But psi may be a sentence, may not be a sentence. It could have this free variable. This is kind of the difficult bit. Well, we just kind of keep a cool head and see what comes out. This quantified formula is true, right, in the structure. So for all assignments or valuations, right here, W, in the structure, for VM phi of W. Now this says nothing at this stage because this is a sentence. So it actually doesn't need any assignment to make it true. But equivalently, for all t in I and valuations W, I now have the psi holds. And actually in W, I replace Vm by T. That has exactly the same force as the line above. Right? After all, everything in I is one of these equivalence classes. So all I'm doing is just doing one of these tweaks on this valuation. I'm just saying, okay, the nth place will return this object in the domain. So again, everything in here comes from a closed term. So for all closed terms T in our language, and again, all valuations, I have I gamma proves psi with, I put the term in here in place of, sorry, round brackets, term in place of Vm. Again, and the comment I make is every object in I here is the denotation of such a term like this. So to quantify over all objects in I is the same as quantifying over all terms T here. If and only if. For all closed terms T in the language. Now I've got sentences here. I've substituted in for this free variable, the only free variable of psi, this term. So this is now a sentence. Now I can use the inductive hypothesis. As this here is a sentence. Okay, so this would essentially do it. Right? I'll let you look at case one. I deliberately skipped it because it was the easier one of the two. So why is this? Why are we done? Right? We want to show this if and only if this here. We still haven't quite finished case two yet. So suppose it's not the case that gamma proves phi. So we're doing this direction here. Suppose gamma does not prove phi. By completeness of gamma, gamma proves not phi. Phi is this for all Vm psi. So gamma proves there is some Vm such that not psi. Now we deploy fullness. This is where fullness is used. So for some constant, gamma proves not psi. The constant is substituted in for Vm. Now we use the equivalence that we just proved over here. I've got a constant substituted in for Vm. So this sentence here, this will get me back to what I want. So by the equivalence we just showed, right, it's not the case then that I here is going to be a model of phi for all Vm psi, because here's something which gamma proves the negation of here. And then in this direction here, if gamma does prove phi here,
So was that a user contrapositive then?
yeah, so here this was contrapositive, yeah. We assumed this and we got, we assumed not this and got not that. Here we are. Not this, got not this. But if gamma does prove phi here, so again, this is for all Vm psi, then by axiom A4 of our rules of predicate calculus, gamma will prove psi for any term put in there, with the caveat that the term didn't have free variables Vm. And so again, by what we just proved about this sentence here of lower complexity than phi, so again, by the above, my gamma here, right, is going to prove this phi. Because again, everything in the domain of I gamma is the denotation of one of these t's. So this actually is the end of case 2. And the induction. So that's the end of that lemma. Sorry, that's gone on over time, I realize. So we'll get from this, we've done all the technical nitty-gritty stuff, and so from this we'll then get the completeness theorem. So that will be.
Is T a closed term?
See, sorry.
Is T a closed term? No,
T is a yes. So T. Well, no, it doesn't actually. Doesn't actually have to be a closed term. At least for this part, we can apply the axiom as long as Vm is not one of the free variables here. But we are thinking about these as being closed terms. Yes, I suppose I'm saying here, the axiom doesn't require T to be a closed term, but actually we're using closed terms here. Okay.
What if Vm is a free variable of T? Is that possible?
No, I'm just saying that, I mean, the objects in the structure I gamma are all equivalence classes of closed terms. I'm just, to go from here to here, I'm applying axiom A4, which this always works, right? As long as the Vm isn't one of the free variables of T. That's all I'm saying here. But actually, Vm isn't one of the free variables of T because T is a closed
Oh,
term.
okay. So that's just like a statement of the axiom.
Of this axiom A4. I'm just saying this is a legitimate move because Vm isn't one of the free variables of T. T doesn't have any. The T's we're interested in don't have any. Okay, so we'll finish off the completeness theorem tomorrow morning.